Hello, I'm Kazuto Takashima from Kyushu Institute of Technology, Japan. Today, I'd like to talk about our recent work on fabrication and evaluation of Catheter-Type tactile sensor, composed of two polyvinylidene fluoride films. Catheters and guide wires are widely used in the treatment of infarctions and aneurysms. The point of insertion is often the site, so the catheter and the guide wires must be 1 meter or more in length and less than 1 millimeter in diameter for treatment of the brain. However, as shown in this figure, manipulation of these devices is limited to pushing, pulling, and twisting at the proximal portion outside the human body, and the procedure is very difficult due to the small diameter and tortuosity of blood vessels. Moreover, the surgeon's visual and tactile perceptions are severely reduced during manipulation in such surgeries. One method to improve manipulation of the medical device is measurement of tactile force between the medical devices and the vessel wall, such as excessive contact force. Moreover, tactile sensors can detect the stiffness and shape change in tissues caused by disease. Namely, the sensor enables palpation in vivo. Organic ferroelectrics such as polyvinylidene fluoride, PVDF, its trifluoethylene copolymer, PVDF trifluoethylene, and VDF polymer exhibit piezoelectric responses that are useful for tactile sensors. They are promising materials for Catheter-Type tactile sensors because of these characteristics. Therefore, we developed a Catheter-Type tactile sensor composed of a PVDF film. In a previous study, we fabricated a prototype Catheter-Type tactile sensor composed of a PVDF film with an outer diameter of 2 mm. In an insertion test using a blood vessel model with region-like shapes, the prototype sensor output corresponded to the shape of the inner wall of the model, making it possible to determine the position of protrusion and the convexity interval of our last surface. However, this sensor can detect only a uniaxial contact state. Therefore, in this study, we added a piezoelectric film to allow the sensor to detect a biaxial contact state. We evaluated the frequency responses of the proposed sensors. In this study, we made two prototype sensors, samples 1 and 2. This is a photograph of the prototype sensors. The size of the prototype sensors is also shown. Because we manually fabricate the sensors, the sizes are different, like this. This is a schematic diagram of the prototype sensors. First, we created a resin mold using a 3D printer. At the base of the prototype, we poured silicon rubber into the mold using a tubing pump and vulcanized it. This is the fabrication process of sensor. We adhere the PVDF film number 1 with an elastic binder as shown in this figure. We connected the film electrode to a cable using a conductive adhesive. Next, we rotated this prototype by 90 degrees and fit into the mold, and created a silicon rubber base to fit the other sheet of PVDF film could be affixed as shown in this figure. Then, to detect the force in two directions, we affix the other sheet of PVDF film number 2 in such a way that the two PVDF films bisected each other at right angle as shown in this figure. The two films were adhered to transmit the sensitive deformation to PVDF film number 2 as shown in this figure. Finally, we completed the prototype by covering the PVDF film and cable with silicon rubber. As shown in this video, when the sensor was bent by a force applied at the chip, the PVDF films shifted from neutral plane, becoming compressed or stretched. To evaluate the sensor frequency responses in the present study, we used the experimental apparatus and indenters as shown in this figure. The base of the tactile sensor was affixed in a jig. The chip was vibrated by an indenter attached to a shaker, and the output of the PVDF film was measured. The output voltage of the sensor was acquired by an oscilloscope via charge amplifier. The tip was vibrated along the 1 and 2 directions shown in this figure. This is the enlarged image. The sensor and the indenter in the vibration experiment were filmed using a high-speed camera to check the contact between them. The displacement of the indenter was measured from above by a laser displacement sensor. In this study, the indenters were used to increase the distance between the sensor and the shaker to reduce the effect of the electrical noise generated by the shaker. Indenter 1 and indenter 2 were prepared as shown in these figures. These tactile sensor behavior at 100 Hz vibration. As shown in this video, indenter 1 frequently separated from the sensor in the preliminary experiments. Therefore, indenter 2 was used in the experiments, as shown in this figure, under the assumption that the sensor acts as an elastic cantilever. When the tip of the sensor is bent, the output current I from the PVDF film can be expressed by this equation 1. From equation 1, the following equation is obtained. The displacement Y applied by a shaker at the frequency F can be expressed by the following equation using a constant Y0. Differentiating both sides of equation 3 and substituting the result into equation 2 gives the following equation. With the amplitude in equation 4 denoted as I0, the following is obtained. Because the value of K in this equation is determined by the sensor size, PVDF material properties, and other factors, I0 over Y0 is proportional to the frequency F. In this study, substituting the actual values into equation 2, we obtain these values. Using these values, we calculated the theoretical values of I0 over Y0. In this study, experiments were performed 3 times each at frequencies in the range of 10 to 1000 Hz. A first Fourier transform was performed in this experiment on the obtained sensor output and displacement to exclude the effect of electrical noise. The amplitude of the sensor output and the tip displacement I0 and Y0 respectively were found at the applied frequency. These are experimental results. These figures show the sensor output I0 and the indenter displacement Y0 respectively. Although the displacement decreased with the increased frequency due to the characteristics of the shaker, the sensor output increased like this. As shown in these figures, the prototype sensors could detect 2-axis displacement. Prototype sensors measure the height displacement of less than 0.1 mm in the high frequency range. From these figures, we calculated I0 over Y0 values. The theoretical values calculated from equation 5 are also shown. As shown in these figures, the measured value of I0 over Y0 increased gradually with the increased frequency. The measured values for PVDF film number 1 are similar to theoretical values, whereas those for PVDF film number 2 are smaller than theoretical values. An improved sensor structure is necessary to transmit the deformation to PVDF film number 2 in a future study. In these figures, for sample 2, when the numbers of the PVDF film and the vibration direction are the same, the sensor output is large. That is that the sensor has a directional sensitivity and can thus detect a biaxial contact state. In contrast, for sample 1, although the vibration direction affected the sensor output, the effect was small and the magnitude of correlation was not constant. One reason for this is that sample 1 was thinner than sample 2, as shown in these photographs. To evaluate the frequency characteristics in more detail, these figures show the frequencies that maximize the sensor output in the range of 100 to 1000 Hz. In these figures, it is desirable for the gradient to be 1. As shown in these figures, in this range, the frequency at which the maximum output is obtained from the sensor mostly matches the set frequency, indicating that normal output is obtained. On the other hand, in the range of 10 to 90 Hz, the frequency did not match the set frequency. One reason for this is that the sensor output was small in this range because I0 is proportional to the frequency f, as shown in equation 4. In conclusions, in this study, we fabricated two prototype catheter-type tactile sensor composed of two PVDF films. We evaluated the frequency responses of the prototype sensors. Our sensor has directional sensitivity and can detect a biaxial contact state. The measured values for the PVDF film on the tip were similar to the theoretical values. That's all. Thank you very much.